Assalamualaikum and hi, my name is Muhammad Harib bin Muawiyah and today I will be present about lab project presentation by group 5. Title of experiment is torsion test. This is our group members and first is myself, Muhammad Harib bin Muawiyah, number matrix CD24037. Number 2, Muhammad Iwan Hafiz bin Rosli CD240240. And number 3, Muhammad Rafi bin Abdul Rahman CD240108. And the last one is Muhammad Nur Ikram bin Anam CD240096. For the list of contents, we have introduction, experimental theory, experimental equipment, experimental procedure, additional theories, result observation, calculation, discussion, and conclusion. For introduction, torsion tests allow direct measurement of the shear modulus of a material. Torsion testing, although not as common as tensile testing, is a useful complement for determining mechanical properties. Type of torsion experiment: torque control. Uniformly increasing torque is applied to the specimen. Strength is measured as the angle of twist. Angular speed control. The specimen is rotated at a specific angular speed. Torque is measured during the rotation. Experiment type for this study: angular speed control. The directly measured quantity will be torque. Relationship between Young modulus and shear modulus, where V is a Poisson ratio. Determining E from the experimentally obtained G reinforce their independence. Next is experiment theory. Pure torsion occurs when a circular shaft is twisted at either end without any other force acting on it. Left hand end of the shaft fixed, right hand end of the shaft rotate through an angle B relative to the left hand end. You can see from the figure 7.1, a longitudinal line on the bar surface rotate slightly to a new position. A rectangular element between two cross-section distant dx apart become distorted due to rotation. It shown separately in figure 7.2. During torsion, the right hand face of the element AB DC rotates. Point B and D move to B and D. Key point is side length of the element remain unchanged. Angle at the corners are no longer 90 degrees. The element undergoes pure shear. The shear strength is Y is equal to the decrease in angle at corner. Next, the shear force acting on a small element of area dA is proportional to the local shear stress. The moment of this force about the center is where G is shear modulus, theta angle of twist per unit length, and P for radial distance from the center. The total torque T is the summation integration of all such element moments over the cross-section area. The integral P square dA is known as the polar moment of inertia. And the last one for experimental theory, GJ is called the torsional rigidity of the shaft. The total of angle of twist psi over the shaft L length is theta equal psi over L. Therefore, T equal GJ psi over L. By measuring the torque and angle of twist theta during the experiment and knowing the shaft dimension, we can calculate the shear modulus J. For a solid circular shaft of uniform radius, the polar moment of...
Okay, next for experimental equipments. So we have 3 equipments that we use. Okay, for the first torsion testing machine. Okay, torsion testing machine, the purpose is to measure a material resistant to twisting and calculates the torsional strength, shear modulus, and other related mechanical properties. Then for the test type, applies a torque to a specimen, typically a cylindrical rod or wire, and measure the resulting angular displacement to evaluate the material's behavior under torsion. Then for the second equipment that we are used, vernier caliper. Okay, for vernier caliper used to measure the length, width, depth, and also internal and external diameter of the object with high accuracy. Okay, for the third one, the torsion specimen. For the torsion specimen, we have two types such as brass shaft and also mild steel shaft. For the brass shaft torsion specimen, for materials properties, brass is a metal alloy primarily composed of copper and also zinc. For tensile strength, typically range from around 350 megapascal to 550 megapascal. Then for the shear modulus, which is G, generally around 40 and also 45 gigapascal, thought it can vary depending on the specific alloy. Then for the ductility, brass is a relative more ductile and can deform under stress without breaking, which make it ideal for torsion testing, where material deformation is observed. Then for mild steel shaft torsion specimen, for material properties, mild steel is a type of low carbon steel, typically containing around 0.05 until 0.25% carbon. Then for the tensile strength, range from about 400 megapascal until 550 megapascal. Then for the shear modulus, which is G, usually between 75 gigapascal until 80 gigapascal, which is higher than that of brass. Then for ductility, mild steel is more ductile than brass and can undergo more extensive deformation before failure. Okay, for the experimental procedure, first of all, we have to record and measure the specimen length and diameter at 3 different locations and calculate the average length and diameter, and also measure pulley length, and also we have to fill up the table 7.1. Then for the second procedure, we have to mount the specimen to testing machine and test the specimen lab. The lab technician and or your lab instructor will help with the right procedure. We have to make sure pulley is in horizontal position. Then for the third procedure, we have to attach the angle indicator and zero readings. Then for the fourth procedure, we have to measure the angle of twist when load, which is W, is added from 0 to 200 Newton, and when load is removed from 200 Newton to 0 Newton for both specimen. Fill up table 7.2 and table 7.3. Okay, for additional theories, we have 4 theories. Okay, for the first one is Sound Venom's torsion theory. For circular shaft under pure torsion, cross section remains plane and undistorted. So this is only rotate. If rotate. For the second point, supports the use of simple shear stress formulas in our test. For the second theory, torsional rigidity, which is the symbol is GJ. Okay, for the first point, represent the shaft resistant to twisting, and the second point is related to the slope and of the torque versus angle of twist graph. For the third point is higher GJ means less twisting for the same torque. Then for the third theory is fatigue under torsional cyclic loading. For the first point, repeated twisting even under small stresses can cause material fatigue and failure. And for the second point, important for rotating parts like shaft and axis. For the four theories, plastic torsion theory. For the first point, after the elastic limits, shaft can undergo full plastic deformation across the section. For the last point, not observed in this experiment since loading stay within the elastic region.
Assalamualaikum. I'm Muhammad Arikram bin Anang, matrix number CD240096. I'm going to present about result and observation. Result, table 1.1, diameter of specimen. Shaft that had been given to us is brass and mild steel. Diameter, D in mm, millimeter. We had to measure the shaft in 3 different locations. For the length, we need to measure 3 times. For the brass diameter, first location is 6.3 millimeter, second location is 6.3 millimeter, third location is 6.3 millimeter. The average for diameter will be 6.3 millimeter. For the brass length, first measurement is 75 millimeter, second measurement is 75 millimeter, third measurement is 75 millimeter. The average for length will be 75 millimeter. The next one is mild steel. For the mild steel diameter, first location is 6.3 millimeter, second location is 6.3 millimeter, third location is 6.3 millimeter. The average for diameter will be 6.3 millimeter. For the mild steel length, first measurement is 76 millimeter, second measurement is 76 millimeter, third measurement is 76 millimeter. The average for length will be 76 millimeter. Last one is poly length, which is 80. Second is table 7.2 torsion test result for brass shaft. The load W in Newton N had been given 0 Newton, 50 Newton, 100 Newton, 150 Newton, and 200 Newton. We need to measure the angle of twist during additional and removal of load. The first one is angle twist during additional load. For 0 Newton will be 0 degree, for 50 Newton will be 3 degree, for 100 Newton will be 6 degree, for 150 Newton will be 9 degree, for 200 Newton will be 12 degree. The next one is angle twist during removal load. For 0 Newton will be 12 degree, for 50 Newton will be 12 degree, for 100 Newton will be 10 degree, for 150 Newton will be 7 degree, for 200 Newton will be 2 degree. The last one is table 7.3 torsion test result for mild steel. The load that had been given still same as before. The first one is angle twist during additional load. For 0 Newton will be 0 degree, for 50 Newton will be 4 degree, for 100 Newton will be 6 degree, for 150 Newton will be 9 degree, for 200 Newton will be 10 degree. Next is angle twist during removal load. For 0 Newton will be 10 degree, for 50 Newton will be 9 degree, for 100 Newton will be 8 degree, for 150 Newton will be 6 degree, for 200 Newton will be 3 degree. Observation. There are 9 observations in this lab that we had been observed. First, initial torque angle relationship. Both brass and mild steel specimens showed a linear torque versus angle of twist relationship at the beginning. Linear behavior observed due to Hooke's law, shear stress is proportional to shear strain in the elastic region. Second, elastic strain behavior. Materials in the elastic region recovered their original shape upon unloading, indicating elastic strain. Third, twist behavior at 200 Newton load. The angle of twist increased proportionally with the applied load until reaching approximately 200 Newton for both materials. Brass shaft exhibited a greater twisting angle compared to mild steel under similar loading conditions. Fourth, material comparison. Brass deformed more because of a lower shear modulus. Mild steel exhibited higher rigidity and strength, resisting twisting more effectively under the same load. Fifth, unloading phase and hysteresis. Minimal hysteresis effect observed during unloading. Unloading path closely followed by the loading path, indicating little to no permanent deformation. Sixth, material failure observation. No visible cracks or material failure appeared at maximum load, proof that testing remained entirely within the elastic zone for both materials. Importance of accurate measurements. Accurate dimension measurements were critical for calculating shear stress, shear strain, and modulus of rigidity. Even small measurement errors could cause significant variations. 8. Testing equipment performance. The pulley system functioned properly. Angle indicator measurements were trustworthy, ensuring reliable data collection. Last one, 9. Agreement with theory. Test results align well with the circular shaft torsion theory. Confirm that material deformation is highly dependent on shear modulus values.
For the calculation, the first one is torsion constants. So the formula polar moment of inertia is J equal pi d to the power of 4 divided 32. For the shaft brass is 6.3 millimeter. Then J equal pi open bracket 6.3 multiply 10 to the power of negative 3 close bracket and to the power of 4 divided by 32. So the answer is J equal 1.547 multiply 10 to the power of negative 10 m to the power of 4. Then the shaft for my steel same 6.3 millimeter. Then J equal pi open bracket 6.3 multiply 10 to the power of negative 3 close bracket to the power of 4 divide 32. So the answer is J equal 1.547 multiply 10 to the power of negative 10 and 4. Same answer. Okay, the second one is we need to save the torque. So the formula for torque is T equal WR. For the brass, the diameter is 6.3 millimeter. So 6.3 multiply 10 to the power of negative 3 meter. For the radius is 3.15 multiply 10 to the power of negative 3 meter. So torque for 200 Newton, then T equal WR. So we need to search 200 multiply 3.15 multiply 10 to the power of negative 3. So the answer is 0.63 Nm. Then for the shaft my steel same also, diameter is 6.3 millimeter. So the answer is 6.3 multiply 10 to the power of negative 3 meter. Then the radius same also 3.15 multiply 10 to the power of negative 3 meter. So the torque is 200 multiply 3.15 multiply 10 to the power of negative 3. So the answer same also 0.63 Nm. Okay, the third one is angle of twist in radian. So the formula is angle of twist equal angle degree multiply pi divide 180. For the shaft brass, when at 200 Newton, angle of twist equal 12 degree multiply pi divide 180. So the answer is 0.20 die radius. For the shaft my steel at 200 Newton, angle of twist equal 10 degree multiply pi divided by 180. So the answer is 0.175 radius. Then lastly, we need to search shear modulus or G. For the shaft brass, G equal open bracket 0.63 close bracket multiply 75 multiply 10 to the power of negative 3, close bracket, and divide, open bracket, 1.547 multiply 10 to the power of negative 10, close bracket, then multiply 0.209. So the answer is 1.461 GPA. Then for the shaft mild steel, G equal, open bracket, 0.63, close bracket, and multiply 66 multiply 10 to the power of negative 3, close bracket, and divide by 1.547 multiply 10 to the power of negative 10, close bracket, and multiply 0.175. So the answer is 1.769 GPA. Okay, we go through the discussions. Okay, the question is, if the cross section of shaft is not cylinder, explain how to perform the torsion analysis. Okay, the answer is, the first one is, determine the cross section's geometry and whether it is open like an I-beam or closed like a rectangle tube. The second one is, torsion formulas can be used to approximate basic closed sections such as solid rectangles. This requires computing the torsional constants J or K, which is distance from the polar moment of inertia employed in circular sections. Okay, the third one is, when analyzing open or complicated cross sections, shear stress distributions and warping must be taken into considerations, and then analytical approaches such as branch stress functions and numerical methods such as finite elements analysis (FEA) are commonly utilized. Okay, the fourth one is, modified torsion formulas can be used to compute the angle of twist and shear stress while accounting for warping. Okay, next question for the discussions. Briefly explain some of the important factors in designing a high quality shaft. Okay, the answer is, the first one, material selection. Select a material with appropriate strength, toughness, fatigue resistance, and machinability depending on the applications. Common options include alloy steel, carbon steel, and stainless steel. Okay, the second one is load conditions. Understand the several types of loads that the shaft will be subject to, such as torsionals, bending, axial, or mix. This has an impact on both the design of strengths and deflections. Okay, the third one is shaft geometry. Choose an acceptable diameter and length to balance strength and weight. Steps or diameter change should be smooth to minimize stress concentrations. Okay, next, properly install and support bearings and gears to distribute loads evenly and reduce bending moments. Okay, 6. For the 6, limit shaft deflections and frequency to prevent misalignment, excessive wear, and resonance during operations. Then, tolerance and manufacturing. Ensure the design allows for precise machining and fittings, for example, interference or clearance with little mistake. Okay, lastly, surface finishing and treatment. Apply hardening, polishing, or coatings to improve fatigue and wear resistance. For the conclusions, the first one, successful verification. So, the experiment successfully verified material behavior under torsional loading. a load calculation of key mechanical properties like shear modulus, yield torque, maximum shear stress. The second one is consistency with theory. The results were reasonably consistent with theoretical assumptions and demonstrate a high level of experimental accuracy. The third one is issues encountered. Difficulty in specimen alignment. Misalignment may have introduced slight bending strains, possibly compromise result, patients grips slippage. Some would say slippage at the grips observed affected the smoothness and consistency of result. Sensitivity of angle measurement is high, and sensitivity made it difficult to achieve smooth, consistent reading for the angle of twist. Then for the recommendations for improvement, the first one is ensure stronger specimen alignment to prevent bending strains. Use slip resistant fittings to avoid specimen movement during testing. Then carefully calibrate torque and angle measuring instruments for greater precision, and increase the number of specimens tested. Next, averaging across multiple tests will improve validity and reliability of result. Next, overall assessment is the experiment was a valuable exercise for understanding torsional behavior, and lastly, highlighted areas for procedural improvements to enhance future data quality. Thank you.